All right, take it away.
All right. One sec. I need to figure out how to get this away. All right. Can you all hear me?
Yep.
Okay, awesome. Yes, thanks for inviting me. I want to talk about learning to see the world in 3D. And let me try to explain what I mean by that. So this image, I don't know if you recall it or not, but this was a very popular photo on the internet, on Reddit and other places. And the reason it was very popular, I believe, is that when we look at this photo, we all suddenly get this shared sense of helplessness and anxiety. We know there's something wrong and that there's no easy way for us to fix it. But what's really going on in our brain that leads us to form this conclusion that the scene is not in a great state? So when we look at just this set of pixels, just the 2D projection of the world, just a single projection, we can infer a great deal of information about the underlying physical world from these pixels. So we understand the underlying geometry, the different ways in which the different parts apply forces to each other, and how this all leads to this situation. We know what our actions would lead to. So if we open the cupboard, what would happen? We can reason about that. So we can really reason a great deal of information about the world from just very sparse amounts of information. And this is something that we use all the time to solve our very basic tasks. If we move around in a scene, we need to infer the physical state of the scene from observations. If we want to manipulate any scene, if I want to lift my bottle here, I need to understand the geometry and then figure out how to actually manipulate the physical world. So the goal of my research is to enable computers to do the same thing. We want to build AI systems that can also infer the physical state of the world from similarly sparse amounts of information. And just in the way that these inferences help us in performing our tasks, the hope is that these would also help robots achieve the tasks that we designed for them, such as navigation and manipulation, where you want to interact with the physical world. And then there are many more applications in computer graphics. You want to create new forms of imagery, edited versions of imagery, and for that, we first need to reason about the underlying physical world, its intrinsic parameters, such that we can manipulate them. And then also in virtual reality, where you want to enable immersive applications, and then there are many, many more applications. So with that, let's get into the problem statement. We have a single image with us, and we are trying to reason about the underlying physical world, let's say the underlying 3D scene that resulted in this image, that this image was a window to. So we can use the modern machine learning toolkit. We can say that a neural network will solve our task. We'll give this image to the neural network, and at test time, it will give us the scene that we desire, and that's going to be it. Now, even if you believe this, there needs to be a way to train this neural network. So one way could be to use supervised learning. So we collect lots of data, paired images and the corresponding 3D scenes. And at training time, we ask the neural network to be close to the 3D scene. And at test time, of course, we don't need it, and the network will perform the inference perfectly. The problem, of course, is that we don't have such data. So we don't have this paired data, and that's because we don't really have data for the 3D scans. How do we collect 3D scans, right? We need cumbersome, bulky 3D scanners with multiple cameras and light sources, and such custom scanners will definitely not be able to capture the entire diversity of the real world that we observe. So that's not easy. And another interesting thing to note is that we did not need such structured scanning setups to reason about the 3D world. We could just move around as infants and interact with the world, and we could use those observations to really understand the world. So there must be a way to avoid these structured scans, these ground truth scans to train the methods. So if we cannot really rely on the supervised learning algorithms, can we do anything? And we can, I will show you. But for that, we need to understand the domain that we are dealing with, and need to understand the way the world works, the way light propagation works, and how images are created. And this is not very difficult to understand. An image is, of course, captured by a camera that captures the 3D scene. And the image formation process, if you're familiar with graphics, we have done a great deal of work, and we can formulate that mathematically in the form of a physics-based renderer. So just a small picture into how this works. So if you have some scene geometry and the light sources in the geometry, so the light rays originate from the light sources, they would hit the geometry, go to a camera, and the camera would record the image, and that's what we really observe. So the forward process of how once we have the 3D description, how is an image created, that's computer graphics, and we have really mature models of image formation that we can use. What we're trying to do here is the inverse problem. We have the image, but we don't know what the underlying 3D scene is. We're trying to estimate where are the light sources, where's the geometry, where's the camera, questions like that. So even though we don't have 3D scene description, but that's what we're interested in, we can still use the information about how light formation, image formation works to create better learning algorithms. And we can do it like this. So we had this neural network that gave us a 3D scene. And as we discussed, we don't really know what to do with the 3D scene. How do we tell the network what a reasonable 3D scene is? So what we can do is we can use our physics-based renderer, which does not have any learnable parameters. It's just simulation of light, and we can use that to create an estimated rendering from similar conditions as the input observations. And then we can just evaluate how close the estimated rendering is with the input image. So if it is very far away, we for sure are doing something wrong, right? Because the correct 3D reconstruction should lead to an image that looks identical to the input image. So it cannot be a large error. What if it's a small error? So ideally, if the error is really low, we should be able to confidently say that this is a good reconstruction, but in practice, that does not happen, and that's because this problem is ill-posed. That means that there are multiple solutions of 3D scenes that can all perfectly explain any given image, right? So this is a 3D scene that perfectly explains this input observation. It's just a plane that is textured with the image. I mean, as I rotate it, you see that it's just a plane. So this perfectly explains it. And then on the bottom, this is a reconstruction. In this case, it's not a plane. It has some volume of the object. And this also would explain the image, but they're very widely different 3D scenes. And there's like an entire infinite family of scenes that can all match the image. So match really the objective of the learning framework that we designed. And not all of these are great, right? So when you looked at this image, I bet you were thinking something in your head, you had something that resembled more the second result and not the one on the first. So that's also geometrically correct, but that's not really what we had in our head. So there's some solutions that are more likely than others. There's a space of probability, how likely scenes are. And the first one was not that likely, and the second one was much more likely. So our learning framework as it was could not distinguish between these, and this was flawed, and we need a way to tell the system which ones are more likely than the others. Okay, so how do we do that? Well, I showed in my early research that you can solve this easily by using videos. So monocular data sets would not have this information. It has these ambiguities, but in a video, we can resolve these ambiguities to a large degree. How do we do that? We have the 3D scene. We're trying to reconstruct one frame of a video, but what the video allows us to do is to supervise the reconstruction of that one frame against other frames of the same video. So the other frames would correspond to different scene conditions. So let's say the camera moved between the two frames. The first one was taken from here, second one was taken from here. So if the reconstruction, we reconstruct the first frame and we evaluate it against the second frame. So if we reconstructed the planar scene, it would not look correct from the other viewpoint because that's not what real world scenes would look like. So videos as supervision allows us to eliminate a lot of the ambiguities that we otherwise observe in monocular training. And the interesting thing to note is, of course, we don't need the videos as inputs to the neural network. The neural network can perform inference on the sparse single view information. The videos act as supervision, as supervisory signal that allows us to constrain the solution space further such that the other unlikely scenes are not considered during training. So I used this in my research to perform 3D reconstruction of human faces. Here you see on the left is just some, I'll show you frames, images. In the middle, there's reconstruction of the geometry. So just the face geometry overlaid on the frames. And on the right, it's all components. So it has appearance, lighting, everything that should completely describe the input face. All the reconstructions are done frame by frame. So there's no, the network does not get to see the video at test time. I'm just showing it as a video. Right. Okay. So now the question is that it turns out that we can reason about faces using videos as training. But the question I had in my mind was that to what degree are we limited to modeling faces? And if the principles are very general and they seem to be general, can we really go ahead and model the entire diversity of the world now? So that's what I tried next. We're going to use a very similar framework, and we're trying to not limit ourselves to human faces, but try and tackle more general scenes. We're going to do something very similar. The framework will look very similar. The training data is going to be videos, just as in the case of faces. We're going to make some assumptions that go beyond what I had for faces. So for one, I'm going to assume that there's going to be no scene motion. So in the case of faces, as I'm speaking, my expressions change my face geometry. So it's a non-rigid setting. So I'm not going to deal with such settings for the general case. I'm going to assume that there's no scene motion and the scene is static. And the other thing I'm going to assume is that I know the camera pose for every frame. So the only thing that can change is the camera, and I know where the camera is in every frame. This is, again, something that we didn't need in the previous case, but we do now because we are in a more challenging setting. So this is how the training videos end up looking like. These are some of the data sets we use. So you can see that the scene is static, nothing really deforms, only the camera moves from frame to frame. And I'm going to assume that an oracle gives me the position of the camera in every frame. With that, the training framework is going to look very similar. We're going to take one frame of a training video, reconstruct the 3D scene. We're going to evaluate that scene against the same image using physics-based image formation. And then we're going to also use the same 3D to evaluate against a different frame. In this case, the different frame, again, only depends on, only differs with respect to the camera position. So all we are doing is taking the 3D scene, rendering it from the camera pose of frame 1, and then rendering it against the camera pose of frame 2, and making sure that it looks correct from all the different viewpoints. So if we do that, we get results like this, where on the left is the input image. On the right, I'm showing you renderings. Once I have a 3D scene, I can create new images from different camera viewpoints, and this is what that looks like. So whenever we are in a part of the scene that is completely observed in the input image, it looks fairly good. But as soon as we go beyond the parts of the scene that are directly visible, we get this really blurry result. Here's another example. This is a fire hydrant. And again, from the visible parts, it looks reasonable. As soon as we move behind the hydrant and we try to look at the back side, it's again very blurry. And this blurry result is not ideal. We cannot really use it for any application like in robotics or graphics or anything. So what's really going on here? Why do we get these blurry results? The answer is uncertainty. So if I show you an image and I ask you what the back of this fire hydrant looks like, do you think you will be able to correctly answer that question? And I believe the answer is no, I cannot at least. Um, the answer is that we don't, the reality is that there are these pixels in the input image simply do not contain sufficient information for us to uniquely determine what the correct answer is. So if I show you these three options and I ask you to pick one, it's very difficult to pick one because all three could be possible solutions. We know what properties the image from the back should look like, what properties the image should have, but we don't know exactly what this image would look like. So there's uncertainty. But the neural network we have been using so far is a deterministic function. So it can take an image and it can give us one 3D result, whereas the reality is that there is no one 3D result. So in our visualization from earlier, we had this space of scenes with some subset of more likely scenes. And in this case, each one of them are likely scenes. It's not that some of them are unlikely. There are multiple desired solutions. And because the neural network is a deterministic function, the only thing it can do is to aggregate all these observations. Let's say these are the observations it saw during training. It has to aggregate them somehow. And if it does some mean aggregation, it will bring us beyond the space of likely solutions and give us this blurry result. So it's not one of the plausible samples, it's just mean averaging, which is just mean aggregation, which is not useful at all. It brings us beyond the space of any reasonable solution. Okay, so this is what happens in practice, and we need to fix it. We need to design a method that can actually reason about uncertainty and take that into account. One popular way in which people approach this problem is by asking the question whether the lost distribution in this aggregate solution can be recovered in 2D. So we had this deterministic result that was blurry. What about we use a 2D generative model? So generative models have probabilistic nature. So what if we turn the deterministic solution and try to recover the entire distribution of realistic solutions using a 2D generative model? Right? And this is motivated by all the progress that we have seen in generative models in images such as Imagen or Stable Diffusion or DALI, where they take text as input and give realistic images as output. So can these models be repurposed such that they can take the blurry result as input and give us the sharp results as output? So this is a popular approach. What happens is that if we do this, we can get results like this. So what you'll notice is that there's obviously a lot of inconsistency. And if I stop the frame at any particular point, you would see that the images, each of these frames are fairly realistic. They're not that bad. It's just that when we look at the entire video, they look inconsistent. And that is not unreasonable because it is an image model after all, and that image model does not understand that there is an underlying 3D scene that is trying to explain. So every time it gets this blurry image, it can convert it into a realistic image, but it's not going to be the same image, the image of the same scene when we move the camera. And this is not exactly the same method. I've jumped around a bit, but overall, in a very high level, this is what these methods would give you. Now, this is not the best result that this line of work would have. You can use video models, it would get better. You can take these models, you can extract some consistent 3D scenes out of it. Those results are also very impressive and very promising. But ultimately, there needs to be a step where the 2D models are used where you can get inconsistent results. So if I look at the scenes before, like in this distribution of all possible scenes that can exist, a scene like this, in my opinion, is an impossible scene. There cannot be a 3D scene that can exist in reality such that when we observe them from these different viewpoints, it leads in inconsistent results like this, right? So there wouldn't be any scene where you look around the scene and you would get such inconsistent results. So you can do something about it later, but you would have to go through this step. So I'm going to show you a method which does not have to face this weird limitation. We will look at a method where we can directly learn a distribution over 3D scenes, and we will never have to generate an impossible scene in anywhere in our method. Okay, so this is what we're going to do. We had this method where we could take this deterministic neural network and use it to convert the image into a 3D reconstruction. And now we're going to change it and make this a generative model. So the generative model now is not going to give us just a single deterministic solution. It's going to give us a way to sample from the entire distribution of possible, all plausible scenes that are consistent with the given image. So it's now going to model this distribution of P of S conditional on O, where S is the scene and O are image observations. The generative model can include neural networks. The important thing is that this is now a probabilistic model that can sample as many scenes as you want from the underlying distribution. You can use the renderer now to generate the any image from the underlying scenes, any reconstructed scenes from the conditions of the input observation. They should all look identical, but as we go beyond, they should differ, and they should all be plausible scenes. So before I show you how the conditional model works, I want to explain how an unconditional model over 3D scenes would work. So the difference is that now we're only modeling P of S rather than P of S conditional on O. So there's no O observation in this case. We just want to learn the prior distribution over 3D scenes. And once we go over this, we can go back to the conditional case because that's what we're really interested in. Then we can look at the results. So the generative model that I'm going to show you is also based on diffusion models, the same generative modeling technique that is used for Imagen or DALI. Here's a brief primer on how those models work. Let's ignore 3D for now, and let's consider that we're building a generative model over images. So our image observations are O, and we are trying to build a model that can model P of O. So a generative model's goal is to transform a distribution that is very tractable, let's say a normal distribution, and convert it into a distribution that resembles P of O. So we want to sample from a normal distribution, this noisy image, and we want a way to transform every sample from this normal distribution to a sample that looks as if it could have been a part of the training distribution. So diffusion models perform this transformation using a series of denoising steps, where we take the noisy image, we remove a little bit of noise from that image, then we remove a little bit more noise, and we keep doing that until we go to a very clean state. And this clean image should resemble, should be a sample from P of O. This is the goal. We want to be able to denoise it in such a way that in the end, we go to a sample from P of O. How these models learn it is very interesting. So there are two interesting aspects. One is that each of these denoising steps, so there's an iterative model, and each of these denoising steps can be learned independent of every other step, and then we can simply stack them on top of each other at test time, and that would give us reasonable reconstructions. And the other thing is, how do we really learn the denoising operation? So the most common way of doing it is to use a neural network. So a neural network takes a noisy image and it gives us an image that is less noisy. How do we train this neural network? That's not very difficult. So you can take samples from the distribution that we're trying to model. So in this case, we're trying to model a distribution of images. So we take training samples, training images, we add noise to the image, and that becomes the input to the neural network. And then we can add less noise to the image, and that becomes the supervisory signal for the output of the network, right? So a loss function looks something very similar, where we want the output to look like the ground truth. So this is a supervised learning problem. Okay, so this is the overview of how a diffusion model would work for images. Once it is trained, we can sample from noise and get to realistic images. So can we use the same thing for 3D models? Answer is no, because we don't really have 3D data with us. So in this case, if we want to model 3D distributions, we would want to model P of S, but we don't have any 3D data. Our premise has been that we can reason about 3D only by looking at 2D observations in the form of images and videos. So if we do not have 3D data, we cannot really add noise to it and generate the input to the neural network. Nor can we figure out what the output should look like, right? So we're stuck. We don't really know what the input should be, what the output should be, and we cannot really train these models in the way we're used to training them. So now I'm going to introduce a framework that we proposed recently, which would allow us to do this, which would allow us to build models over 3D distributions where we do not ever observe 3D data directly. And it's going to be a modification of these models. So let's look at it in more detail now. So one of these denoising steps, let's isolate that now. And I'm going to make a couple of changes to this model that would allow us to do this. So the first change is that instead of the neural network directly giving us the denoised image from the noisy image, it's now going to give us an estimate of the underlying 3D scene, right? Once we have the 3D scene, we can do what we've been doing so far and use our physics-based renderer to create an image that is completely clean. And then we want to match the input-output behavior to the previous settings. So we're going to add some noise explicitly to this. And now this looks identical to the previous case. So nothing really has changed. The input-output behavior is identical. What has changed is the internal structure of the neural network that's performing this transformation. So instead of the neural network directly giving us the denoised image, it's now going to give us a 3D scene. We're going to simulate light through the scene to get us an image, and that's how we get the denoised image, right? So even though the input-output behavior has not changed, we have made an important addition to the framework, which is that now the model is forced to only generate images that a valid 3D scene can represent. It cannot generate by design any impossible scene. It's not in the solution space of the model's search space, right? So that's good. We have figured out how to limit ourselves to producing images that only valid scenes can represent. But we haven't really changed the objective. The loss function remains identical. We're still training them on monocular images, just as we did in the case of images. So all the guarantees that we can make about the distributions are still about P of O, and we cannot really make any statements about P of S. And this makes sense because if we supervise only with monocular images, we know that there are ambiguities. We can still have these kind of solutions where you have implausible 3D geometry that can still explain our images. So we have eliminated impossible scenes, but we haven't really eliminated implausible scenes. But we know how to do that. We have looked at it earlier. What we're going to do is train on videos instead of monocular images. And now we're going to add video constraints. So we're denoising one frame of the video, and the 3D scene that we get in while denoising that one frame, we're going to supervise it against a different frame of the same video. And this will limit ourselves to only plausible scenes. So the loss function now has an additional term. The original diffusion model had the term that the denoised image should look like the ground truth, and now we have the additional term that the image from another viewpoint should also look like the ground truth. And with this change, we have a framework which is 3D structured. So as I said, like only can generate 3D scenes that are possible, that can exist. And the multi-view supervision limits ourselves further to plausible solutions. And with that, now we can show that the model now is optimizing for the distribution over the underlying 3D scenes. We're optimizing for P of S. We are not just optimizing for P of O anymore. We can write mathematical statements about the framework. So if certain conditions are met, I'm not going to go into detail, but I just wanted to show that it is possible to write mathematical statements. The proof is in the paper. I'm happy to talk about it later. But we can, and we do mention, we write mathematical statements such that if there are parameters of the neural network such that the loss function that I showed you is minimized, that the distribution we would recover would actually be the true distribution. Right. Okay. So let's look at how we actually implement it. So we have the noisy image. As I had mentioned earlier, we know the camera poses that correspond to every image. So we have this camera, we have the image, then we have the neural network that gives us some features, and these features parameterize an underlying 3D scene. So this is the underlying 3D scene that the feature parameterizes, and it does so implicitly. So if you take any 3D point in the scene, we can project that point onto the feature plane. And then we can look at the sampled feature there. We use a separate neural network that can transform that feature into the 3D quantities that we're interested in, which are the color and density values in this case. So the 3D scene representation is a neural radiance field, if you're familiar with it. And this conditional way of modeling the nerve condition on an image is borrowed from pixel nerve. So this way of like taking feature maps and retrieving 3D scenes as a function of the feature map. So this is borrowed from pixel nerve. Okay, so we have this way of getting to color and density values, and we can do this for every 3D point in space. Now, when we have that, we can also render images from any other camera viewpoint. So let's say this was the input camera, and we want to generate clean images without any noise from the same camera. So we simply shoot rays from every pixel that corresponds to this camera, sample many points along the array, compute their color and density values, and perform an integral that corresponds to the volume rendering integral. And this gives us the color value at that particular pixel that we shot the ray from. We can do that to generate the entire image through different pixels. And then if you want to generate an image from a different camera, it's trivial. We now simply trace rays from that camera's origin. That's how we get any other viewpoint as well. So it's really a 3D representation that allows us to physically generate images from any viewpoint. What we looked at so far is one of the denoising steps. Some noisy image comes in and some denoised image comes out. We have looked at it earlier that we have iterative process where we would like to feed in completely noisy distribution sample from normal distribution, and we would want to iteratively transform it into the clean observation. So we're going to do that here as well, where at every step of denoising, we're going to use that 3D structured neural network. So we're going to take the noisy image, we're going to compute 3D, we're going to project it back to get a cleaner version, and then we're going to lift it again to 3D and then keep doing this again and again. This was the unconditional model. And now, as I mentioned earlier, what we're really interested in is the conditional version, where an image goes in and we want to only recover the distribution of scenes that agree with this image. So in this case, all we need to do is to add an input image as a conditional to the neural network that we're looking at. Sorry. Right. So that's the only change. And with this change, we can show that you actually learn the conditional distribution. Right. So the actual implementation also is very simple, where the underlying 3D scene, the feature map that we compute now comes from the noisy feature map, as well as the feature map that comes from the input image. Okay, with that, we can look at some results now. So this was the deterministic result I showed you earlier, which was pixel where visible parts look okay, the other parts don't look good. And this is what our results look like. So we recover the distribution. This is just one sample from the distribution. And you can see that it's not as blurry as the result you saw in pixel. It's a reasonable looking scene that is sharp. Because we have the distribution, we can look at multiple samples. We at this particular viewpoint, I'm just moving through the different samples in the scene. Right. And you can see that it's quite diverse. It's a challenging setting. Kitchens can look very different from each other, but the model still seems capable to learn that distribution. We also see the variation in the depth maps. And the model was trained on RGB videos, but because we perform 3D reconstruction, we can also perform geometric reasoning, such as by computing the depth maps. This was the other result with the fire hydrant, which was blurry, and now this is our result. So again, looks sharp. It's not the mean aggregate result. And we can again look at the distribution of the different results. So you can see that there's a lot of uncertainty in the appearance, but also in geometry. You can look at the depth maps and it keeps changing. All right. These are some more results. Let me just focus on a few. So in this case, image of a bedroom. We walk back and the model tries to reason about the geometry and appearance of the 3D scene that could exist behind the image. The same in the opposite direction. So you walk in a room, there's occluded parts, and the model has to reason about what is occluded again. And you can see why this is useful. Let's say a robot has to plan. It doesn't need complete observations to begin with. You can already start reasoning without having a perfect set of complete observations. Right. So just a very quick summary. We have generative models now that can model the 3D states of the world. We did this by building structured neural networks that have information about what the 3D world looks like. We used physics-based priors in the form of physics-based renderings. And in terms of data, we needed videos to train these models. While the particular application was on 3D reconstruction and computer vision, I think what this kind of framework shows us is a way to solve a specific class of inverse problems. These are problems where we are trying to reason about some underlying structure from some observation. And we have the idea of what a forward model looks like. So we know something about how observations are created from the underlying structure, but it does not need to be a unique structure that creates any particular observation, but we still know some idea of what the forward model is, and we're trying to figure out what the underlying structure is given any observation. And I think there are many possible applications for such frameworks. For example, here's one that I think could be interesting. This is cryo imaging, where we are imaging some biological matter, and what we're interested in is the 3D structure, but what we get to observe are just 2D projections. So very similar to what we looked at earlier. And given any projection, we have to really understand what the underlying structure is. I believe this, as well as many other applications in different fields, would fit into the framework that we have been looking at so far. Very generally in computer vision, I like working on models that are structured and try to reason about or try to figure out how much physical information I can actually inject in the models. The reason I find that this is promising is, first of all, it allowed us to reconstruct these structured quantities without supervision. So the self-supervised methods, just because we figured out how we told the networks how the image formation works. This allows us to simulate unseen scenarios. For example, we never saw a fire hydrant from the top, but because we could reason about the 3D structure, we can actually reason about how it looks like from very out of distribution viewpoints. And if we can do that, I'm curious about how much these models would advance, for example, generalization and downstream applications. So if we have the structure, we can reason about out of distribution viewpoints. Can we also move our other computer vision tasks, such as high level reasoning, and can those also generalize to these viewpoints? And then controllability is a direct result of such structured models, where you get these intrinsic components of physical world as explicitly as outputs. Um, because we told the models how the world really works, how image formation works, I believe that they're more efficient learners. So even in a world where a lot of data, a lot of video data, by modeling them, a model without these inductive biases could learn what the underlying physical laws are in ways which the world works. But I believe that by actually injecting this information, these models would very likely be more efficient learners. They would not need as much data as would otherwise be needed, right? So it doesn't need to relearn the universal laws of nature. Um, Especially useful in domains where we do not have access to large data sets, such as scientific applications, possibly. And in those domains, if we don't have large data sets, we really have to think about what other structure models can we build to for more data efficient learning. And as a very one sentence summary, this I believe is the best of scalable deep learning models and physics-based models. We do not need to give up on either of these ideas. We don't need to go to deep learning and completely forget whatever information, whatever theories we built about how the world works. And we also don't need to abandon deep learning and just use the physical-based models of many, many decades ago. So some way of combining the ideas of these different strategies. All right. So this was the work that I wanted to show you. And this is just a couple of slides on what I think are interesting directions to move on from here. So just going back to this image, we really didn't solve this problem. I motivated that we'll build these models that will allow us to reason about complex scenes like these and allow us to do causal reasoning where we can imagine what would happen to the scene, condition on any actions that we take in the scene. But we're not there yet. We're still very limited. We could do some geometric reasoning, look at it from different viewpoints, possibly reason about occluded surfaces and so on, but we're still quite far. And a lot of the reasoning that I described to you earlier requires some understanding of dynamics. And the constraint that we have placed on our model so far is that the training data should be static. There should not be any motion that is in the scene. So training videos look like this. Is the examples from real estate 10K data set that we used for training. And you can see that this is very unnatural. Our real world does not look like this. It takes a lot of effort to assemble data sets like these where nothing is moving really, and this is not what a person sees in their life. So I think it is very important, both for reasoning about dynamics, but even for building more generalizable models that can look at more data without really us curating the data too much, is to reason about motions. And this is really an open problem. How do we model scene motion in 3D? What kind of data and learning frameworks we need to understand motion? And this is a big open problem. As I said, like this will allow us to reason about more complex scenes. It will allow us to use more data, but it will also allow us to reason about some dynamics, such as intuitive physics, in ways that we can do so easily. So if I ask you, where is this ball going to go next? we have probabilistic models in our head that can tell us that, oh, one way or the other, like these are the possible options, and we can build similar models in computer vision as well, where we can understand what the probabilistic inference over physical states can be, over future physical states can be. There are many other kinds of inferences that are very interesting, but understudied. For example, if I show you this image and I ask you where the sun is in the scene, that's a trivial task for us. We can look at the shadow and we know where the sun is. But this really simple task is not that simple for the computer models. Our model, for example, does not cannot reason about this. It will either give a very geometry with a lot of artifacts, or it will just not work well. And that's because we don't model these interactions of light that result in creation of shadows. So how we can enable that is another direction that I'm excited about. And the final thing I wanted to mention is that scenes, especially, are not just monolithic reconstructions. We are treating them as this like one scene goes in and there's like one reconstruction, one global reconstruction that comes out. But in reality, a scene is made up of all of these different objects that are composed together. Each one of them have their own independent properties that are shared with other parts of the scene. And this is something that is very important, but something that I don't know how to deal with really well right now. There are some results that of other works that I've done recently that go somewhat in this direction or related directions, where this is, for example, for dynamics, where this is an input scene where there's a fan blowing some air on the scene, and you see the leaves moving just very slightly. And if you manage to reconstruct the motion in this scene in 3D, we can enable reasoning like this, where you apply an unseen force into the scene and see how the scene reacts to that. So just by modeling some small amount of motion, we can already enable reasoning like this. So I'm very optimistic about going further in this direction. And then I've been mentioning so far about how we can solve this task really well, but I want to formalize that and really understand to what degrees can we solve it really well, how do we do it, and in what ways are we different from the way the vision models actually perform this task. And then I didn't go into the applications of these kinds of reasoning. So of course you can have a lot of interesting computer graphics applications where you want to edit scenes. This is a example where you formulate constraints and then see the scene react to those constraints. And then there are applications in robotics where you want to actually go and manipulate the physical world. Okay, so hopefully you're convinced that there are many applications of trying to enable physical reasoning of the world. And then there are many other applications that I didn't go to, ranging from simulation for other applications, for simulation for to compute training data for other applications, to all the way to scientific applications. I just wanted to acknowledge my mentors and close collaborators that were part of the works that I showed you. And with that, I'll end my talk. Thanks.
Thanks, Ayush. Are there any questions?
I guess I'll just ask you a quick question. Yeah, really nice talk and exciting work. You kind of touched on what my question was at the end, but I was wondering just what happens actually if you were to run your method on a scene with motion, like somebody walking. What does happen right now?
We trained our model on static scenes, which means that there were no people in these training scenes. So the model just simply does not understand humans. I think it would just give some garbage results with no reasonable geometry at all. If you were to train the same model on dynamic scenes with motion, I think you would get blurry results where you're trying to fit a static model to a dynamic scene, and you would just like get the average blur of all the dynamic components, and that's what the model would also do at inference. But currently, the model that I trained, if I showed it humans in the scene, I think it would just give garbage results, not even anything reasonable.
That makes sense. Well, thank you.
That's